Right, so I think we can start. So then from code thing, we'll talk about the Linux RISC, it's getting late, Linux bug hunting, the RISC-V realm.
Yep, so hi, welcome. This is talk about, let's say, RISC-V Linux bug hunting. We're going to go with a couple of bugs we found while working on RISC-V, how we went through, go through this down there. So we'll go through looking into the bugs, how we fix them. Some of the techniques we use aren't specifically RISC-V, but we thought let's be relevant to the topic. So a little bit about me. So I'm a senior engineer and fellow at CodeThink since 2012. I work on mostly Linux, QEMU type things. So nice little context, slideshow. As an introduction, this is going to be a tale of two bugs, and I sort of threw a bonus one in, which is similar to one of the other ones. While I said in the description of this talk we were going to do this out debuggers, we are going to use a debugger for one, and I promise no live demos because we know how all those go. We will also learn, hopefully, a little bit about the RISC-V architecture. So the first one, I think this is chronologically the first one we found, is a kernel user access bug. So we'll start with the bug report. So if you know that there is a testing system called syzbot that goes through a number of different architectures, it's an automated system which looks for bugs with things like stress testing. And we got this bug report on the mailing list about a user space process causing a kernel oops. Now, obviously, user space processes shouldn't be causing kernel oopsies. So this is running kernel stress test. I have a little bit of the first part of the bug report of the oops there. I'll show some more about this. So the kernel actually provides quite a lot of information about what happens when things go wrong. This is not the old days where you'd be lucky to get the registers and then possibly some weird guru meditation fault and you really didn't know what was going on. We at least have now some good inbuilt Linux debugging. So this is output. So it starts with, at the top, well, it's telling you what happened. So, and this is a very specific error report. So it's not like it tried to access some memory that didn't exist. This is the kernel trying to get access to user memory improperly. We get the information about what CPU it was on, which process was running. We get some information about what hardware. So this information is very easily passed around to people to say, if you're looking at it, what was going on here. We get information about what the build was. And then after that, we can see information about where in the kernel the code was running. So the EPC is basically where the processor core was executing. So we know it's in scheduled tail. There's a return address, so it tells you where it came from, so you can look at how it was called. And then we get register dump, which I've sort of curtailed for space reasons. And we've got some very nice projectors here, but even that, I think people would be straining to read anything lower. And we have information about the processor core status. So that tells you a little bit about what the hardware is reporting, such as status bits, the actual bad address, and a cause info. So you can go into the hardware ISA manual and go, this is actually what it meant, if you would like to. You get a call trace, assuming that information wasn't mangled, because occasionally bugs, if you call into bad code, not always will you get that info. So you get quite a lot of information. So actually, can we go from this information to actually go through and work out what happened? So the basics of this, well, this is a very specific type of bug. So if people know in written device drivers, the kernel is not meant to go randomly wandering through the user memory. This is obviously usually a sign of some problem happening. So RISC-V, like some other architectures, has protection for that. So the kernel has specific copying functions to access user memory. There's checks in to check that that's properly used. So, for example, the kernel has a copy to user, put user, get user. Those are where the kernel should be getting its memory. So one thing we could think about for this bug is that somebody used a bad pointer somewhere. So, for example, just to go into this feature a little bit more, each CPU core has a status control status register with a flag called SUM in it. SUM stands for permit supervisor to user memory. When this flag is set, it obviously allows it. If it isn't set, then you get this specific fault. So we can also say that this fault isn't looking at a bad memory page, because that memory page must exist to be able to know it's a user page. So it's not somebody passed a bad pointer in and the kernel couldn't see it at all. So we have the basics. We know that how this bug is happening. The report also gives us the kernel git ref and config used to build it. So we can go away, build the same binary. So we could either look into the binary code, make a test system of our own and rerun it, because one thing we haven't really known here is whether this is actually reproducible on real hardware. Could it be a bug in QEMU itself? I mean, we haven't really looked into whether that could be the case. However, we were going to do a reproduction case on, say, I think it's going to be a RISC-V, one of the Sci-Fi Freedom machines, but I don't think we ever actually got around to it, because when we started looking into the code, we decided, so look into the code, we can read the assembly output. I mean, it's not always possible to reproduce exactly the same binary, but we can hopefully get to something fairly close. So we, being of old school type of debuggers, think that, you know what, let's not even try. And on this case, the bug was so intermittent, which is another thing that we can say is information into our bug hunting, is that we're not really going to get a lot out of attaching a debugger to this, because it's happening every few hours. We're going to be looking for a lot of data. So we're going to go, firstly, we can disassemble the code, because we obviously love our RISC-V assembly stuff. And we could go and look at the code and say, actually, what's happened here? So we can take the bug report and go back to the code. So we're going to use the GNU obj dump. We can dump the code out, look at roughly where it was. So we can use the output from the ups to go and look at the schedule tail function here. Obviously, there's a lot of information removed just to make this clear. So I've highlighted in the bold area the user access code. Just as a note, the kconfig allows you to add a lot more debug information into the objects. So by default, I don't think it turns that on, but it allows you to do things like cross-reference these instructions to roughly where they were produced in the source file. So in here we have schedule tail is fairly simple function, and the only place it actually looks to go into the user is if this current pointer is set. So if this pointer is set, it's doing something when it schedules, and on the code here we can show that that's the area of code roughly relating to the put user. So we've read through that and go, well, that's fairly simple. So actually, what is this code doing? So I'll go through a little bit of actually what the code is doing, so we can actually work out whether the code is right or not. And actually then, okay, is where we crashed where we think it is. So first thing, we load the S2 register with the sum bit, which we can verify from the ISO is correct. I mean, if this wasn't correct, really we wouldn't have a working system at all. Well, sorry, going back, if the put and get user code was not correct in the first place, it would be very unlikely we ever get a working system. So much of the kernel relies on this that you'd be lucky to even get to a init process. So we'll go through a little bit about this segment. So as I say, S2 is the sum flag. The CSRS instruction, well, that's going to set into the status register to ensure this bit is set. So we know fairly much this bit should have been set when the code happens. And this store word is where it crashed. Now, obviously that correlates with it was storing something. We know that it was storing a value. Doesn't really matter what the value was, because S1 is the pointer to where it's going to store, and we can verify that as well with the crash, saying that's what we look like. And then at the end, it's clearing that flag again. Well, that's fairly simple. It should have worked. I mean, if S1 was wrong, we should have gotten a different page fault. The page fault we're getting is an access problem, but that shouldn't have happened because that bit should have been set. But what's the bit in the middle? Now, I didn't put the actual code mapping in here, but there is definitely something else going on here. This is not a simple set a bit, store a value, clear a bit that really should have happened for the put user. So what have we got here? Well, actually what seems to be happening is that the compiler has shoved our call into our put user code the call to actually get the task process ID. So it's the call to task PID number NS, which you'd think be fairly simple, right? So that shouldn't have been a problem. But clearly this is the only opportunity we have, unless our core has magically gone wrong, that we could have had a bug. So we can read through that code, and I'm not going to go through that code because it turns out it actually does quite a bit. I mean, we've already discounted the bug for being the set child TID. We have only the task PID VNR current call, which calls into the kernel's PID code to go, what is the process ID of this task pointer? Because the kernel has these task pointers that say, this is its representation of a thread. So it needs the actual number to give to user space. But there's no sign in there that there should ever have been a change to this flag. In fact, there's no call to that. So, a little bit perplexed. So what we could do next? Well, the fairly much easiest thing would be just to wrap this call in something that says, on exit to this call, is the SUM flag still set? And you know what? Occasionally, it's not. So what's going on here? Well, we did two things. Firstly, really the only thing that we can probably assume that's happening here is that it's a task, it might get scheduled out. Scheduling doesn't happen so with the preemptible kernel and various things, scheduling would happen at most places. So we can make a fairly good bet that it's task switch. But task switch, you shouldn't unset that sort of stuff, really. So actually the first thing, which was really easy to do, and this was about 40 lines of code, was we started another kernel thread, which went, I'm going to just sit here, sleep for a little bit, check for some flag being set, because it shouldn't have been, and every so often you get this little thread would inherit the sum flag from somewhere. So we've gone through, we've written a test case or two, we've worked out this, so we're fairly sure now that the problem is with a task switch. So the RISC-V switching from one thread to another somehow has completely failed to consider that this flag ever needed to be saved. Now, with fairly small kernels, you don't have a lot of code for these segments of, say, doing a process lookup, but things like the syzbot use kernels that are run with a lot of checking involved. And it turns out the more things you add into the, say, the RCU, etc. parts of the kernel, the bigger the code becomes, and therefore the highly likely that it will get scheduled. So this was something that hadn't been seen, hadn't been looked at. So how actually would we go about to fix this? Because really it's not going to be very interesting if we just leave this bug around. Firstly, this is stopping tests running, because obviously if your test is failing with an oops, that's a not very good test, and it then fails. So first idea, well, task switch code is available. Just save the sum flag into the task info. That was actually, I think, the best way of sorting this out. Turns out everybody likes arguing about this sort of code, and it got sort of sidelined, and I think it still hasn't been fixed. This could actually be a problem down the line, but nobody has run into it yet. There are places in the kernel which use quite wide access to user, so they say explicitly, I'm going to do a lot of movement of memory to user space or from, enable it, do things, disable it explicitly. Whereas in these macros, put user is really just enable user access, put the thing which is probably going to be a word, byte or whatever, disable the access. So the quickest fix here is just to reorder the macro. So this is the patch that actually got accepted for this. It's a fragment of it. So the first thing you do is move and explicitly say a temporary called val. Yeah, it could be value, but you know, it's just as good as the x being the argument. Really, people. Anyway, let's force it to be evaluated before, and then we'll use that value in the actual putting of user, and we can verify that by going to look at the code again. I'm not going to show you the code because it reordered it, it moved that outside the area of checking. This actually generally fixed the problem pretty much, because we now only have a very small window, and occasionally these code get called with the preemption disabled, so it can't switch anyway. This is also pretty good for everywhere else, because we could have also fixed a number of other issues where code could have been called without the user space access being called, because who knows where else this was. I was too lazy to go around and find out any other places, but obviously if we find one, there may or may not be others. These are sort of bugs that happen because people don't think exactly how things get ordered, and the compiler still may well be within its rights to reorder this. I'm not a compiler expert, and having had attempts or two at looking into things like GCC, that hurts my head, and I would rather other people sort that out for me. Thank you very much. So, a quite little bonus side investigation I did, and this is a project we're doing at the moment, because we're extremely strange and weird people. We've been running RISC-V Big Endian. I submitted that talk but it wasn't accepted, so I'm going to get it in here. So we actually have a project. It's on our website. I think we're going to do a blog post about it. We have pretty much a working system running RISC-V Big Endian, but as part of that we went through a few issues. We won't talk too much more about it, but the init code was failing for us. Certain things were failing with stack frames going weird. Now, we could have gone through this with debugger again. It wasn't too early in the system, but we can again go through the code. We know that the thing is failing. It takes us a bit more time on this one, so I haven't included the code because it's like 2 or 3 pages. So what was happening is, because RISC-V runs instructions always little endian, because who cares what instruction endianness you have? You're only really caring about data. It turns out people like hand assembling instructions, because who doesn't? So apparently the pause instruction, when byte swapped by data, turns out to be a valid stack pointer movement. Wow, that was not fun. Anyway, that was a complete and utter side quest on things. As you can see, sometimes you can go do things with or without a debugger. We will talk a little bit about tracing, but again, that's sort of things that are really useful for long-term problems. So our second one, user legal instruction. So I'm told that FD SDK is actually meant to be called Free Desktop SDK. We put in some effort on Free Desktop SDK, help things like build. We have some runners. The build fails with SIG-IL. Now this is repeatable, so this is a case where actually, you know what, let's go with a debugger. GDB is actually useful for something, especially when you can get a very repeatable problem. So I've seen the log, got the log, last bits of the log from the bug report. You say bin bash. Well, why bin bash is dying, but illegal instruction gets run. The whole build just stops. Repeatable on most architectures. However, some of the runners are not showing this problem, but we can repeat it. We know we can repeat it, and we've repeated it on our own hardware. So we run our job under GDB. Backtrace is at least useful. In this case, we actually get a backtrace. We know where the problem is. SIG-IL. Okay, so it's in something called ABSL, which is libabsale. We can dump the really intensely unuseful function name. Thank you for C++ for mangling the hell out of that. But it's executing read cycle. That's an instruction that gets into the register A0, the number of cycles the core has run since I think it was reset. Obviously, if it can disassemble the instruction, and it's known to have been good, why are we getting an illegal instruction from it? Well, this is where my colleague would let me bing that for you. This is why I don't try and talk to him very much. But your favourite search engine is actually one of your friends here, because actually this is a known issue. Searching for it actually finds a really good bug report as well. So the problem here is that read cycle, like on a few other architectures where information like this is a security problem, well, since Linux 6.6, this has been disabled. Now, security reasons, and I won't go into all the sort of security problem leaks that happen from this sort of thing, but it's been disabled. We can't use it now. Why libabsl is using it to read the time is another matter. The number of comments in the thread about the bug report may show a few slightly less favourable feelings about this. But we have get time of day and we have clock get time. They're fairly good. These have been efficiently available since probably the time of Linux 4 via the kernel's quick syscall interface. So why on earth libabsl does this is another question. Anyway, newer libabsl has stopped this because obviously they've realised this was a fairly silly thing to do. I mean, I'm all for efficient coding, but that isn't a great example of it. So this is a really easy thing to fix. There's two things we can do here. Since Free Desktop SDK, we can control the build because it's all declaratively built. Just replace the damn thing. Use the newer version. If we couldn't have done this, we can use the SBI PMU driver that has a sysfs control, which was not intuitive, so I didn't actually get it to work, to re-enable this for user space, because if you don't like security and you can control your machines, who cares? Right, so we fixed that. Good. Everything runs again until it crashes. Right, so further discussions on this problem go, well, we must have another bug. Somebody posted, this is what my runner showed in the D message. Okay, so that's raw hex. So as humans, I don't like raw hex very much. It basically is the program data, the program instruction data showing hex. The current program counter is there. I can't be asked to run a 2-hour job to find out what the hell is going on. You can turn this into some nice little text. And because I don't like decoding code from hex and we think we have better things to do, just feed that into GNU-AS. So we can use the same upstamp before, and it's there again. So I won my bet with Javier. It was the same bug. I don't think I got any payment for it, but nope, it's the same bug in the same library. Because gRPC includes its own copy of libabsl. Jeez, really, guys? Anyway, the fix there was to go and change the build again to tell gRPC to use the currently local copy. So, after a day of shouting at people, we actually got the builds going again, which was great. So we had some builds. Obviously, the actual cause of the issue was upgrading from the runners from 6.6 at some point. Some of the runners may not have either been updated properly. I failed to check what exactly all of them were. Maybe some of our architectures don't obviously honour the disablement of read cycle. Not sure. However, because we are absolutely insane people, I went, you know what, this shouldn't be too difficult to fix the hard way. Because we're in slightly weird, we can actually add a check into the illegal instruction handler. So the kernel, the low-level code, when it gets an exception, calls into some C code. That obviously in RISC-V kernel is called dotrap ints illegal. It gets past some registers about the state of the code. Now obviously this is code that either goes through and goes, what you did was incredibly silly, and prints your instruction dump and oops, or delivers a sigil or whatever to your process. But we know what, we could actually check whether that bug was read time and emulate it. Only issue, nothing in Arch RISC-V has done this before, so we'll do a little bit of a quick run through what that would do. It also seems to be a bit of a hack. So I did actually put this on the Linux RISC-V kernel list, and people were either shocked or went, what on earth have you done that for? That is probably a reasonable response. So if you don't know how instructions are specified, RISC-V, like most others, has some sort of way of packing bits out to say, these are bits, certain bits do this. So each subset of bits say you have some sort of operation code, and then what that operation is doing with data. Obviously, people generally don't do much with this. It's usually compilers for you. So just as a dump, we're looking at the system group, which is the ZICR extension, which gives you a whole pile of ways of getting at control and status registers, which read cycle is one of them. So you can do this CSR read, gets your register. So if anybody's interested, this is what I did, roughly. There's a little bit more because there were things that we were missing. But it goes, well, is this instruction that was fetched a system instruction? If so, we can then go and decode some more information from it. So there's helpers in header files, because obviously some people need to look at instructions for other things, like if you're a trap. So you can go through, extract. We can say, is this our CSR read and set? If so, we can look for access to the cycle register. And because the instruction, the instruction traps are designed to allow you to restart if it had to fix something up. We can just basically say, into the registers that we were passed from our task, set the RD from the CSR time. Obviously, we don't want to use CSR cycle, because whilst we could get that from the kernel, that would be just leaking the information we didn't want leaked. CSR time is obviously apparently a better way. So we can just move the EPC register on to where it was, return. So just to say this, we end up having to do some little bits of support. Maybe some of that will get merged. There was no actual set register, there was get. There was no way of extracting one of the subcodes from that. And obviously we had to do a little bit of messing about with the instruction. So, but it worked. We did write some test code for this as well, because obviously you would like to test. So we did a whole pile of test code. The result was, as I said, we sent that to the list. Nobody liked it. Now, that wasn't entirely unsurprising. It was more of a proof that it could be done. I was bored, and it would be maybe useful for somebody in the future who might actually need to do this, either to fix up some legacy code, maybe something in the future needs sorting out. Anyway, it's going to be left out there. People could look at it if they like. It is entirely silly thing. It was about, I think with the test code, it's a couple of days of work. So the conclusions, right? So did say a little bit about that. So in conclusion, some of this, great, 5 minutes. Yeah, padding this out, the extra buggery, got that linked up. So in conclusions, this may not be as easy as just using a debugger, but for cases where you have some really difficult bugs, it can help as a different way. It's very old school. This is how I would do it back in the ages when, say, the old Acorn stuff, the Amiga. But it's really useful to look at it. Sometimes it's just useful to look at the code and try and understand what it's doing. In this case, in the case of the user access bug, it was very clear that the code looked fine. It was just that it was ordering it wrong. The kernel also has a lot of useful logging systems nowadays. For instance, if your bug isn't causing a crash but is definitely repeatable, there's a lot of kernel logging. You can use it to efficiently export data from the kernel and log it elsewhere. For instance, I had a problem with a Tegra DMA controller. Now, every few hours you'd get a blip in the audio. Nobody could quite understand why. So really just add a couple of trace points to the DMA driver where it was looking at things like moving on to buffers, reporting position. Things like that in the DMA driver that were probably where it was going to be. Export that data via the trace and just export it off the system. You can look at it later, analyze it. So running it overnight just showed that there was a bug in the positional parameters when there was an occasional buffer swap and parameters were not often updated in the way we expected. So there was basically just a check needed and you could then do that. So I say this is probably old school, but hopefully was interesting to people. I haven't got around to releasing the slides. I didn't get time to get these formatted out. Our designer decided to change a lot of our formatting on the last minute, so yeah. Hopefully we'll be putting them up. I don't know if there'll be somewhere we can put a URL for that. Anyway, hard question. I'll make a blog post about this or something, but we have a couple of slides of references. These are like the issues, some kernel code, testing, blog posts. We had a number of mailing list discussions. It's always nice to have people weigh in on stuff and then go, well, you know what, actually, why on earth did I start talking about this? So, thank you. And hopefully it might have been at least something interesting and may have given you an idea about alternative ways. Obviously, there are many ways to look at bugs, and sometimes just talking to your rubber duck might help. And if you could explain it to a rubber duck, you probably got to the point where you actually understand it. So there's a few minutes left. Don't know if anybody has questions. Oh dear.
Hey Ben, thank you. Really enjoyed your presentation. Thank you so much. Can you describe how your kernel testing works?
So there's a question about how the kernel testing works. So this is not our kernel testing. This is the syzbot project has, I'm not even sure if it's still running at the moment, but that has information, I think, online somewhere. Google will probably give you an idea. It's found a number of issues. If you search through the kernel logs, there's a number of things it's reported and people have gone. It's testing around a wide range of kernels and architectures, so hopefully that answers your your question. That's not bug. Any further? So, great. Thank you for attending. Thank you for, I should say, thank you to CodeThink. Sorry. Oh, there's one more.
Quick one. Just a quick one.
Yeah.
Like, what motivated you to do Big Endian RISC-V?
What motivated us to do Big Endian RISC-V? Well, I was just about to say that my company, thank you to CodeThink to sponsoring me to be here. So I haven't had to pay for my own transport. What motivated us to RISC? So I did an ARM port of Big Endian about 10 years ago, because obviously we're a consulting group, we do things for people. Somebody went, that will cost you $5 million, we'll have it done next year. And I went, I'll do you that for about $500,000, and it'll be ready 2 months now. And obviously they went, we'll take you, we'll do it, great. So we did that, we got actually quite a bit done, got the customer system going, and then they went, no, we're not going to do that. But the next thing is that RISC-V have announced that Big Endian data is going to be available in new cores. I needed something to do. I needed something to talk about, because things to talk about don't come along too often. And more importantly, nobody had done it before. So we went and did it and went, you know what, this is going to be just a quick project. We'll see if it can be done. At the worst, the company might get some blog posts and some talks out of it. At the best, we can try and go to people like Rise and go, my wallet is looking a little bit thin at the moment. Would you like to buy some consultancy services? But yeah, it was more of a, just try doing this. It will be, we'll spend about 4 or 5 weeks of engineering time on it, and it turns out it's actually quite doable. Whether anybody actually takes it on, who knows, but we'll try and get some talks. So that should answer the why on earth we did the Big Endian, and I think time is about up.
Yep. Thank you.
Great, thank you.